Right, so hi, I'm Nicolas Rinaudo. I'm the CTO of a Swedish company called Besedo, where we do online content moderation and quite a bit of Scala. And well, usually when I give talks, I'm a bit uncomfortable speaking in public, so I give talks about easy subjects, such as type classes, they're not bad, or don't use null. But today, this is Scala Word, this is a lot more intimate, so I'm going to go for something really controversial. Property-based testing, they're not bad, you should try them. Before I actually tackle property-based testing, I want to define a few words that we're going to be using through that. So first, software quality assessment is split traditionally between verification and validation, where a nice definition that I've found that I quite like is software verification is the answer to the question, are we building the product right? And software validation is the answer to the question, are we building the right product? Where the difference is verification is what we're doing according to specifications, and validation is what we're doing the right thing to do for that particular problem. And in this talk, we are going to focus entirely on software verification. And software verification itself is split into two different branches. We have static verification and dynamic verification, where static verification does not involve running the program. So you will have formal verification, you will have linting, static analysis, compiling, these kind of things. And dynamic verification, which is what we're going to be talking about, is basically testing. You run the program and you make sure it behaves according to your expectations. And testing is split into three phases traditionally. The first one is to create test cases that you can run, and this is known as the test case generation problem, which we're going to talk about quite a bit. Then you evaluate your program on that test case, and then you analyze the output, which is known as the oracle problem, because once you have the output, you have to decide whether it's the expected output or not. And so we are going to focus this talk on test case generation and the oracle problem, because program evaluation is not all that interesting, or at least not all that problematic. And the first thing I'm going to do is to define a system that we are going to test throughout the rest of the presentation. This is usually known as a system under test in papers and things like that. I might abbreviate it to SUT on a few slides because I don't have room enough to repeat system under test every single slide. So if I say SUT, it means system under test. And when you want to talk about testing, you usually have two schools of thoughts. You give an example that is really simple, like hello world, and a lot of people feel that this is good because you don't get bogged down in the details of what you actually want to solve, and people can learn from it. The other school of thought is that you want to give a real use case so that people can latch on to experience that they've had, problems that they had in real life, and how to use the techniques that we're going to talk about in their actual job. In our case, I kind of went for the first school of thought. I'm going to be using FizzBuzz as a system under test. I'm assuming most of you are familiar with it. FizzBuzz is, well, it's not a very good thing. It's something that people tend to use for job interviews, as tests for job interviews. And the entire premise is that the specifications are incomplete, but you don't know it, and how do you deal with incomplete specifications? So when that happens, if you ever go to a job offer and somebody asks you to do FizzBuzz, don't go in that company, because if the way they try to test whether you're a good fit is by withholding specification information, are you sure that's the kind of company you want to work for? So the specification that we have is you have to write a program that prints a given range of numbers, but for multiples of 3, print fizz, and for multiple of 5, print buzz. And then we're going to implement it. Implementation is not terribly interesting. It's just basically the specifications. So how to check whether a number is divisible by 3 and by 5, if it's divisible by 3, fizz, by 5, buzz, otherwise I. When I rehearsed that talk the first time, when I showed that slide, some people some of the people attending immediately, oh, this is wrong, there's bugs on your slides. Of course there's bugs in my slides. I'm giving a talk about testing. It wouldn't be terribly interesting if my system under test was flawless. So there are plenty of bugs. I think there's a bug every single line. That's normal. Don't let that distract you from what I'm going to say. I'm not actually wrong, or at least I mean to be wrong, so that's all right. The most traditional way people have of testing software is to do what we call example-based testing, which you are going to find I don't like much. The concept is pretty simple. You have a known scenario, you play it under your system under test, and you make sure that the output exactly what you'd expect. So the most trivial example I could think of is this, where you want to test whether list sorting works. So you take a list that's 3, 2, 1, you sort it, and you make sure the output is 1, 2, 3. So that's example-based testing. That's what most people do or have had to do at some point in their lives. And we're going to implement it for FizzBuzz. So this is pretty simple. We don't have to go through the whole code. Just each test, just make sure that, well, is n divisible by 3, then it should output fizz. Okay, so I take 3, which is divisible by 3, and make sure it outputs fizz. Same for 5 and 7, being a prime number, is divisible neither by 3 nor 5, so it should print 7. Run the test. This passes without any problem. I'm quite happy. And I call the client or the job interviewer, show him the result, and immediately he finds a problem. Ha! If I give you 15, it doesn't do what I expected. Now, the problem here is, well, the first problem is the client is a bit of, I don't know the polite word, but he was not very nice with you because he withheld information. He didn't tell you that something special was supposed to happen in the case of divisible by 3 and by 5. And even if you think about it, you're not sure what you should be doing. Should you be printing FizzBuzz or BuzzFizz? Specifications are incomplete. Second problem, of course, is you as a developer. You have implemented the system, and you are going to test what you have implemented, because by definition, if you had thought about edge cases, you would have tested them. So you have tested everything you have thought of, which might not be everything. And in our case, it wasn't, because we haven't tested a number divisible by both 3 and 5. One way of clarifying these specifications, one way of sorting this problem out for good, is decision tables. So I don't know how many of you are familiar with decision tables. Most likely a lot of you have studied that at some point but forgotten about it because it's so simple that we don't think about using them anymore. But I quite like them and I want them to get back into fashion. So it can be explained in a few minutes. Here is the entire decision table for FizzBuzz, where the 2 columns on the left are called the conditions and the column on the right is called the outcome. And so you can read that pretty easily. So if n is both divisible by 3 and by 5, output FizzBuzz. If it's divisible by 3 but not by 5, output fizz, etc. And this right there, in 4 lines, removed the ambiguity in the specification entirely, and it's a lot easier to implement the system properly. The good thing about decision tables as well is they're so simple so that you don't have to write them yourself. You can get your business type people to do it for you. This is a very good way for specifier and implementers to have a conversation because it is non-ambiguous. And now that we have the clear specifications, we are going to fix our system. So the only difference here is that I have added a new case where if a number is divisible by 3 and by 5, then I output FizzBuzz. Run that, update the test. So I want a number that's divisible by 3 and 5, 15, and make sure that outputs FizzBuzz. Run the test, and of course, as you'd expect, show it to the client. Doesn't work because -3 is divisible by 3 but not by 5. It should print fizz, but it outputs FizzBuzz. And here, well, the main problem is, again, author bias, developer bias. You have tested everything you have thought about implementing, which is not everything. It's just everything you've thought of. And you can't prove to yourself that you have thought of everything. So here, nowhere in the problem statement does it state that numbers can be negative. It's just a reasonable assumption to make, or at least an easy one to make. And we've made it, and we failed. And the second problem, of course, is that FizzBuzz has a domain of about 4 billion elements, and we've tested 4. Doesn't seem that representative. And if we wanted to do it that way, and we wanted to test the entirety of FizzBuzz domain, it would take about 27 years if you wrote one test every 5 seconds. So that doesn't seem to scale very well. And that's all I have to say about example-based testing, because well, this is pretty mildly worded. It's great at the theoretical problem. It's just not very good. It's what we all do, or it's what we've learned to do at school. But it's just really very bad. It's a very bad ways of testing software. It's good for regression tests, for example, but not for proper tests. So what are alternatives to example-based testing? Well, one pretty popular alternative is called generative testing, where the concept of generative testing is, instead of running known scenarios, generate random scenarios and check that it works. But see, there's a problem there. How do you check that the expected output is the output you get is the expected output when the input was random? So that's problematic. And one answer to that problem is something that I'm hoping most of you have heard of, which is called property-based testing. Just to quickly see, how many of you know or have heard of property-based testing? Well, that's pretty good. Wow, nice. Do you actually use that, or do you just know about it? Good, good. I'm talking with people who are already convinced, the best kind of audience. Right, so property-based testing is, the principle is that you make sure that your system under test doesn't violate important properties. It is a bit weird because you don't actually check the output. You check whether the output is valid, not that it's correct. An example here is I've written the specifications for the addition. So an addition, which is quite a well-studied problem by now, we've been doing it for a few thousand years now, we know about three very important properties which taken together entirely define the operation: associativity, commutativity, and identity with zero. So with property-based testing, you'd write it like that. For the first one, for example, for associativity, you'd say, for any I, j, and k which are ints, I plus j plus k is going to be equal to I plus j plus k. And you do that for commutativity and for identity, and then you run, whoops, sorry, nope, you don't run that at all. Wrong slide. And this is how property-based testing works. So this is not a terribly interesting example. I'll get to a more interesting one quickly. But first, PBT suffers from one major problem, which is not necessarily inherent to PBT. PBT being property-based testing, sorry. But the problem with property-based testing is that most people come to property-based testing after years of doing example-based testing. That certainly was the case for me. And well, it kind of wires your brain a certain way. You have been used to having an oracle, being able to say, given a result, is it the correct result? And so this leads to bad behaviors when you try to work with property-based tests. And usually the conclusion that people have is that, well, property-based testing, they're nice, but they're a lot of work for not that much benefit. I don't see how I get my return on investment here. So I think they're overrated and I'm not going to use them. Two notable examples of people who reached that conclusion are me for years, and Dick Wall. I hope he's not in the room, but during a Scalawag episode, I don't know if you guys remember Scalawag, the Scala podcast. It was pretty nice. And during an episode of Scalawags, he said exactly what I just said. He tried property-based testing, felt it was a lot of work, and just basically gave it up. Thing is, I could never find the episode again. So I know it happened, but I can't quote my source because I can't find the episode again. But I know it happened because this is how I got into property-based testing, because I wanted to prove him wrong. So I know it happened. If anybody has the episode, I would love to hear it so that I can actually back what I'm saying here up. So the first trap with property-based testing, which everybody or almost everybody falls into, is you try to rewrite the system under test. So here for FizzBuzz, well, FizzBuzz, we've talked about how it worked and how do we test it? Well, intuitively, if you're used to doing example-based testing, what you're going to do is you're going to have a random I and re-implement FizzBuzz and make sure that your initial implementation and your new implementation match. And you wrote the initial implementation, you wrote the second implementation, you're very likely to have the same bugs, or not necessarily bugs, but same edge cases in there. It's also a lot of work, and FizzBuzz is very simple, so it's all right. But if you have something more complicated, it can quickly become absolutely nightmarish. Yeah, rewriting the system under test is a trap everybody falls into, and try not to do that. I will give you tips on how not to do that just a bit later. And so we have rewritten the SUT returner property, run it. It passes, it completely fails to find the bug that we have left. Remember, we have a bug, we have an issue when we pass -3. We'd expect fizz, but we get fizz buzz. So we know there's a flaw in our implementation, and this property did not find it at all. And then another one, which is kind of similar, but not exactly, which is instead of re-implementing the system under test, you try to be tricky and to come up with some sort of oracle. And the usual way to do it, I've done that a lot, is to create a test case class, which contains the input and the expected output. And when you run a property, you just make sure that fizzbuzz of the input is equal to the expected output. First, that's basically rewriting the system under test in a more complicated way. And second, it makes for really complicated code. I have tests that we use every day that I have written and I'm kind of ashamed of, where I have to make sure that the value I generated is in the right threshold, and if it's within these two thresholds, then that has implication for what happens later. It's completely impossible to understand. I have heavily commented that. I have no idea what's going on, even though I did comment it. When I read the comments, I still don't understand it. So this is a really good way of writing a lot of code that nobody's ever going to understand and completely failing to find any problem, because if you run that, you still don't find a problem. So don't do that. This doesn't work, and it's going to make you give up on property-based testing really quickly. In order to find interesting properties about your system, there are a few strategies. And the main one, or at least the first one, is there are a known set of properties that most systems have at least one of. So when you want to start testing a system, go through this set. Make sure that for every item, you might have one of these properties for your system. And that's what we're going to do now for fizzbuzz. So the first one, the easiest case is sometimes you have a correct implementation of your system, but one that is not suitable. This happens, for example, when you want to optimize an existing function, or when you want to refactor some code. You still have the old implementation. It still works. It's not what you want. So you can use that as an oracle. So that's the easiest possible case where you can just run it and compare and make sure that your result is the correct one. Here, for sorting the list, I want to make a faster version of list sorting, and I make sure that for any list of ints, then my sort of that list is exactly the same result as the canonical sort. And this is dead easy, and when it happens, you're really lucky because you don't need to look any further. It's very often used when you refactor your code. So you have this big, massive block of code, and you know how to demodularize it. You tweak it quite a bit, and you want to make sure that you haven't broken anything, or that you haven't fixed anything that you didn't know was broken, because changes in behavior, even if it's a good change, might break production. So using that existing system as an oracle helps you avoid these problems. Right, it's also useful if you want to add interesting properties to your code. So list sorting, you want to make it distributed. You have an oracle, it's perfect. But for fizzbuzz, so we don't exactly have an oracle, so I don't think it really applies here. That's called foreshadowing. We'll be getting back to that later. Validity. Another easy property to check is you can check whether the output of your system is valid, not correct, but valid. So for example, for absolute value, here we could write a property that says, make sure that any value returned by absolute value is positive. It's not a great one, but it's a cheap one to have, and it's quite useful when first, when your return value is not a good type, say it's a string, like in fizzbuzz, for example. It's easy in your code to make a typo and write fizzbuzz or something like that. So it's a very good way to make sure it's a sanity check against stupid typos and mistake. And it could also be useful, an example I'll be coming back to a few times. Imagine that you have to test the Spotify search API, and you don't own the database, so it's really hard to make sure that the output that you get is the expected output because you don't know what the expected output is. But what you could test is if I were to run a search for, say, the Flaming Lips, that the result only contains tracks by the Flaming Lips. If it contains tracks by any other artist, then I have a problem, I have a flaw in my system. So it's kind of a sanity check, which is always helpful to have. And for FizzBuzz, we could easily write one. So for any I, the output has got to be FizzBuzz, or that I. So it's a dead easy property. In this specific case, it doesn't catch anything, but it could have. Then you want to check whether your system has an inverse, which happens, when it happens, is great news because it's a free test where if you, so for example, for the addition, the inverse of the addition is a subtraction. So given any I and j, you want to test that I plus j minus j is equal I. So when you apply an inverse, a function and its inverse to the input, you should get the input back. And this is, it doesn't happen all that often, but when you write encoder-decoder pairs, such as, I don't know if you've used any of my open source libraries like Canton CSV or stuff like that, or more likely Cersei by Travis Brown, you write encoders, decoders, and a way to test whether they work is just get any object, serialize it to JSON, deserialize it, make sure you get the same input. So that's a free property. It works great. And once you have that one, usually you don't need to go much further because you already have a really, really solid test. It's also useful for database testing, for example, or anything that has a state where when you create something, well, creation has an inverse, which is called deletion. So when you create something and you delete it, the system should be in the initial state. So it could be a property that you might be able to use sometime. And in the case of FizzBuzz, well, we don't have an actual inverse because FizzBuzz is lossy, but we have a partial inverse. So for any number that is divisible neither by 3 nor by 5, then I know that the inverse of the value I got is just transforming that string into an int. So for FizzBuzz, I could write this property which says, well, for any number divided by 3 or 5, then that's OK, I skip. And for any number that's not, then make sure that turning the output to an int is equal to the input. That doesn't actually find anything, but it's still nice to have. And just to be clear, this is not the right way of writing partial inverses in Scala check. I'm going to show that later. I didn't have enough room on that slide, so that works. Another important property is, well, I realize I don't know how to pronounce that word in English. Idempotence, does that work?
Neither does anyone else.
OK, so I can just make it up and everybody's going to get it. All right, idempotence, that sounds fancy. So is your system idempotent? So for those of you who don't know what that is, a function f is idempotent if f of x is equal to f of x, f of x, right, for any x. Typically, list sorting is idempotent. However many times you sort a list, you're always going to have the same result, hopefully. And if you don't, well, you have found a bug, and that's what this property is about. And for use cases for if you update something to a given value, however many times you update it, it shouldn't change anything. If you delete a given object, however many times you delete it, it should still hopefully stay deleted. If you read a given object in a given value in an object, so you have a user and you want to read its name in a database, however many times you read that, it should be the same value. So that could be an interesting property to have for some systems. In the case of FizzBuzz, we could kind of write it, but if you look at the code, that's basically invertibility in disguise, sorry. So there's not much point. Other interesting properties, invariants. Does the system under test have a useful invariant? So in the case of list, for example, an invariant would be the list before being sorted and after being sorted contains exactly the same element, not in the same order, but the same elements, which is the test I've written here. So the diff between the sorted and unsorted list is empty. And this can be useful to test mutable systems, for example, where you can't really rely on the state being what you'd expect. But you can always count on the invariants being respected because otherwise, well, you have a bug because invariants cannot vary by definition. A real-life example that I felt was quite fun was John Hughes. Am I pronouncing that right? The man who invented QuickCheck. He had a database problem. His database would crash every week or every month at the same time, restart, and there was a log message somewhere that said database corrupted, and nobody could work out what the problem was. And there were a few man-weeks spent on trying to figure out what the problem was, and then John Hughes got tired of it, and what he did was generate random sequences of input and write an invariant, which is for any sequence of input, then my database should not be corrupt. And then run these sequences of input, and eventually he found a sequence that corrupted the system, and he had a test case that he was able to replay. And the good thing about probability-based testing is that usually it comes with a mechanism to minify test cases. So not only did he get a sequence of comments that would corrupt the database, but he got the smallest possible sequence of comments that could possibly cause the problem. And with that in hand, it took a couple of hours to fix the problem. So I think what he said was, took him about a day to write the test, then maybe 3 to 4 days running the test all the time, and then problem solved. Whereas the companies that use the database had spent weeks trying to fix it and couldn't fix it. And the funny thing is, he found other cases that would cause database corruption. So invariance is a very good property to have when you want to create properties for your systems. Of course, a bit disappointing, but FizzBuzz doesn't really have any invariant that I can think of. And no foreshadowing here, I just can't think of any invariant, and there's nothing that I'm going to say about that later. Your system might have what is called a metamorphic relation. Now, this is a part of the presentation that I'm really happy about, because usually when I give presentations, after I'm done, there's always one of the more experienced speakers that walks to me and says, that was a really good presentation for a first time. And it's not exactly my first time. And then these people would say, just to soften the blow, but what was really, really good about your presentation is you made something really complicated seem very simple, and you made the audience feel smart. But that's not the point. The point is for me to feel smart, not you to feel smart. So, metamorphic relation. I feel really smart here. Now, it's actually very simple, and we're going to get back to that a bit later. I'm going to give you a first definition, which is probably incorrect in all the specifics, but a very good intuition. So, given a metamorphic relation is a couple of transformations, such that if you apply the first one before the system under test and the second one after the system under test, the outcome doesn't change. So this is a bit abstract. A concrete example here would be for sorting lists. If you first invert every number in your list, then you sort, then you reverse the output and invert the numbers, you should get exactly the same thing as the input. And so this example is a bit trivial and not all that interesting, but it should be useful to solidify the intuition. And it's very, very useful in a lot of scenarios. And I actually have a whole section of this presentation about this. So we're going to get back to that later, because there's a surprising amount of papers on the matter. But a concrete example, I talked about the Spotify search API test before. Well, an interesting metamorphic property of search would be, given a search with, for example, for Spotify, I want all the tracks by such artist sorted by date ascending, then if you run it, but you sort by date descending, then you're going to get the same output. Not in the same order, but you're going to get the same tracks. So that's an interesting property to have, and one that actually has yielded bugs in known search APIs that you most likely have used. And I'm going to get back to metamorphic relation in a few slides, because they're really very interesting. And it so happens that there is one for FizzBuzz, and one that immediately finds a problem. FizzBuzz, we know that if the output of FizzBuzz contains fizz, so it's either fizz or FizzBuzz, then we know that the number was divisible by 3. And we know that if a number is divisible by 3, then its inverse is also divisible by 3. So let's turn that into a property. And this is what I've written here. For any I, if FizzBuzz of I contains fizz, then FizzBuzz of minus I must contain fizz as well. and running this property, we find the problem immediately. So I don't know if you remember the code. Don't exactly remember on which slide it was. That was probably something I should have prepared a bit better. Right here. So the problem here is obviously the way I have implemented div3 and div5, which just doesn't make any sense. This is not how you implement div3 and div5. So let's fix that. Now that we have found the problem, let's fix it. So as you can see, I now have proper implementation of div3 and div5. That actually makes sense. I update my property and run it, and now all the tests have passed. So going through that list of properties, of property categories, I have found a few that I could use for FizzBuzz, and conveniently, one that found the problem that we were looking for. So what you do at that point, you have found properties, you have found a set of properties that seems to work, but this is the beginning. This is not where you stop. Now that you have the properties, you have to challenge them. You have to try and fool them. And this part is actually quite fun when you get into it. So what you do, you try to provide the simplest possible implementation you can think of the system under test that fails your property. That doesn't fail your property, that your property will accept. And it's good fun because you find yourself trying to trick yourself. You know exactly what is being tested, so how do you fool that? And in the case of FizzBuzz, if you look at the implementation of the property, it relies on the presence of fizz. There's a hard-coded value in there. So most likely, we can abuse that. And we can, if I provide the smallest, silliest implementation of FizzBuzz that I can, which is one that doesn't handle the buzz case, and then I pass that through this set of properties, which is the properties that we have defined before, validity, invertibility, and stability, then we'll see that this actually passes all the properties, and it shouldn't, because the properties are supposed to be exhaustive. So, as I said before, we know what the problem is, the hard-coded fizz. We don't deal with the buzz case, so we just update the stability property to deal with both fizz and buzz. And at this point, the tests fail as expected, and we have a much better set of properties. So this is how you go from no property, I don't know what I'm doing, to a set of robust properties that will fully test a system. And so in conclusion, property-based testing, it's pretty amazing at the test case generation problem, because there is no test case generation problem. It's random. You eventually are exhaustive on your test domain. It's pretty good at the Oracle problem, provided you know what you're doing. And there's surprisingly little literature on how to identify properties, which is what I'm trying to address here. So you have to get the hang of it. You have to do it the right way. You have to put yourself in the mindset where the Oracle doesn't exist, and this is not how you test your system. But of course, that's a lot of work. So there's a cheat mode. Remember how before I showed you decision tables? Well, if you squint, aren't decision tables kind of specifications and an Oracle for your system? This is the decision table we wrote for FizzBuzz. And if you look at it in a certain way, the two leftmost columns, they kind of look like a generator of your input type. So for example, the first line is telling me any number that is both divisible by 3 and 5. I could definitely write a generator for that. Or any number that is neither divisible by 3 or 5. I could definitely write a generator for that. And the rightmost column looks a lot like an implementation of your system under test, which takes an input and shows an output. So again, take the first line. If the number is both divisible by 3 and 5, then the output's got to be FizzBuzz. So you would decode that as a function from int to a string, which is always FizzBuzz. And the last line, if the number is neither divisible by 3 nor 5, then you would decode that as a function from string to from int to string. And well, the good thing is I've actually implemented that in a proof of concept project that I have that's called Kantan dtables, dtables for decision tables, where first you define your decision tables as a CSV file. That's pretty much a CSV file here. And then you have to do a bit of legwork. You have to write the generator I was talking about before. And this one can be a bit tricky, so I'm going to walk you through it. The first thing I'm going to do is, given any I, return an I that is neither divisible by 3 nor by 5, because if I want to generate a number, to write a random generator that generates a number that's either divided by 3 nor 5, or 3 or 5, etc., then I basically want to have a number that's divisible by neither, and then depending on what I need, I just multiply it by 3 or by 5. So it's not super interesting, but this is how it works. And then you write your condition decoder exactly like you would with Cersei, for example. Where here I'm saying, for the specifications, give me colon n modulo 3 and n modulo 5, give me these values as booleans. And then, well, if I want both divisible by 3 and by 5, I generate a random int. I make sure it's either by neither, and then I multiply by 3 and 5, and I get the number that I wanted. For the outcome, it's pretty much the same thing. Give me the output column as a string, and if that string is n, then I return int to string. If it's fizz, return fizz, etc. And then you just run the test, really, where you say, I want any int, and I want the corresponding system in the test, and I make sure that what I wrote is equal to the output. So the good bit about that is, having written the decision table, not only do you have clear specifications to provide to your developers, but you also have free properties. And the easiest possible properties to test, because you have an actual oracle in the shape of properties. So in conclusion, decision tables, they're a pretty good specification tool when applicable. Of course, it's not always applicable. It mostly works when your system behaves as a pure function. You can also get that to work if your system is stateful, but then you need a state transition table, not a decision table. And when you do have a decision table, then it's a pretty good property-based test tool when you do have it. And very importantly, it's work that somebody else can do. I like it when my business people just give me my test and my specification, and I just have to focus with the actual coding. So this is quite pleasant. Now, I have been explaining how great property-based tests are. There are scenarios in which they're not applicable, or at least initially applicable until you think really hard about it. And one of these scenarios is when generating test cases is very expensive. And so this is something that happened at work a while ago, where the thing that we wanted to test, we had to put a machine learning model that, given a picture, would put a bounding box around the faces. That's me a few years ago, like 20 or so. That's the only picture I could find of somebody who would not sue me for showing it, so that's what I took. And so this is how it works. Given the image, it's going to put a bounding box around the face. And so our data science team worked hard on that, made a really, really good model, which apparently had all the good results, all the good properties. Accuracy was off the charts, very good precision, very good recall. We put that in production and promptly crashed the whole production. So we shut everything down, put it on much more powerful computers, everything booted, tried it again, sent a picture of the CEO, and the answer came back 16 seconds later as dog, which obviously was not great. So, but at this point, what's the problem? Is it the model? Not likely, because they have run, I mean, the data science team knows their job. They have run all the tests. Is it the way I deployed it? Maybe. How do I test that? And one way of testing it, the only way I could think of testing it, is absolutely horrible. You take a lot of images, annotate them manually, and then run them through the system and make sure it kind of works. And that sounds like a lot of work. It sounds really boring. And this example is pretty easy because it's a face. But one of the clients that we have is an online dating site, and one of the rules that they have is they don't want customers to expose themselves on their pictures. And I'm not going to spend days highlighting that. So I want to find something else. And so we thought really hard about it with a team. And somebody, obviously not me, but somebody came up with this fancy idea. If you have this image, and then you change the color palette, the bounding box is at the same location. If you flip it, the bounding box is not exactly the same location, but you know where it's going to end up. If you rotate it, again, it's not exactly the same place, but you know where it's going to be. So the conclusion here is, if you have an annotated image, you can transform it in lots of ways and still know what your output should be. So you could, from one image, get hundreds and hundreds of test cases, which is pretty neat. It's not perfect, of course, because the image here, as you can see, it's still kind of the same, isn't it? This is still only testing. If I have a Caucasian, youngish person, then I'm going to find his face. It doesn't test all the other possible use cases. It's much better than what we had, but it's not perfect yet. And then another person said, but do we really need to have the initial bounding box? Because we have a model that knows where to put the bounding box. So if I were to use that model to generate the first bounding box, then transform the initial image, do lots of stuff with it, and I know where the output bounding box is going to be. And if they match, then the system is sane. And if they don't match, then the system is not sane. And that is basically the concept of metamorphic testing. Transform your inputs in ways that you control and that carry over to certain properties in the output and check that. So if you have a non-annotated image, you can do lots of stuff with it and still know what the output should be. You went from, I'm going to spend a few weeks annotating faces, and that's just for starters, to give me the entire internet, and I can test that without ever looking at a single image, which is pretty neat. At least it means a lot less work for me, so this is the kind of stuff that I quite like. And this is the basis of metamorphic testing. Metamorphic testing was invented by a very clever person called T.Y. Chen. I imagine his thought process went something like, in software verification, failing tests are very interesting because they prove that something went wrong. They tell you that either your system or your test are wrong, but something is not working. On the other hand, successful tests, well, they're pretty useless, aren't they? They just tell you, I haven't found anything wrong. Not, there's nothing wrong, just I have not found a problem. And that's not quite the same thing. A successful test doesn't give you, it might give you a measure of confidence, but it doesn't prove anything. And so T.Y. Chen thought, well, what if I could make successful test cases actually useful? And so he thought about that quite a bit. I'm actually paraphrasing his paper on the genesis of metamorphic testing. I'm not inventing that whole thing. So he thought about that really hard, and he came up with this definition, simplified because the actual definition is a couple of pages of mathematical equations, and I didn't have the room nor the brain to do that here. So a metamorphic relation is a pair of conditions such that if two inputs fulfill the first, then the result of their evaluations must fulfill the second. A couple of examples of that just to solidify it. Well, first, what we've just seen with the faces and the bounding boxes. And another one which comes up quite a bit in the literature is if you have a graph and your problem is to find the shortest path between two nodes in the graph, then the shortest path between A and B has got to be the same length as the shortest path between B and A, provided your graph is not directed, of course. So this is a simple metamorphic property. Just flip the input A and B and make sure that you get the same length. And metamorphic testing is just that. Identify metamorphic properties about your system and turn them into tests. And in truth, there's not that much more to say about metamorphic properties in metamorphic testing. It sounds really intellectual. It's got morphic in the name. It's got to be important. But that's all there is to it. So I still have some time. So I'm going to give you a couple of case studies of metamorphic properties, which yielded very impressive results. The first one, I abbreviated it because the actual name of the paper is Testing Compiler for Equivalence via Modulo Input. Something like that? Something like that. Anyway, EMI. And the intuition that the person who ran the test had was, well, I know how to instrument some code in order to know, upon evaluation, which bits of the code were used, and more importantly, which bits of the code were not used. So if I were to grab some C code, compile that, and run it on some input, and log the output, and identify all the dead code, then I could generate a new test by looking at all the dead code and mutating that in a way that still compiles. Just the compiler has to accept. But it doesn't have to be correct. We don't care because it's dead code. It's not going to have any impact on the output. Turns out it does have an impact this way. The person who ran the study found 79 new unique JCC bugs and 68 new unique LLVM bugs. Those are not software that are obscure or not properly tested. Thousands of people use that thousands of times every day. And there's a lot of tests. But even though there was all this test suite and all these use cases, we still found a lot of problems using metamorphic properties. So if you read the paper, EMI, it doesn't actually mention the name metamorphic properties once, which I assume is because he didn't know about the concept, because it's clearly an application of metamorphic properties. Another case study, which I've already alluded to a couple of times in the past, is testing search APIs, such as Spotify or YouTube. And the idea was, if I run a query and I refine that query, then I should be able to know how my refined result should behave. So if I were to search, say, for all the songs from the Flaming Lips, that's going to give me a set of results. And then if I say, well, I want to run the same search, but for all the songs published after 2010, so that's going to yield a result set that is a subset of the initial one. You don't know if the results are correct. You don't know if all these songs are every single song that are released. But you do know, on the other hand, that if it contains any element that's not in the initial result set, then you have a bug, because the first search was every single song. And you can play with that idea. You can also mutate the pagination parameter. You can say, give me the first time, just give me by pages of 10. And the second time, give me by pages of 100. And then you iterate through the whole thing, get your results, and compare and make sure you have exactly the same thing. You can do that with a sort order, like I said before. And then you can combine all these things to get a very, very wide range of test cases, which found it's slightly less impressive, but still 3 new unique Spotify bugs and 8 new unique YouTube bugs, which, again, those are APIs that a lot of people use a lot of the time. And in conclusion, metamorphic testing is a lot simpler than the name would make it out to be. It's very good for the test case generation problem when PBT is not applicable, because then you can kind of trick it into becoming available for PBT. And it's also fairly good at solving the oracle problem when you don't have an oracle, but you know that you have a metamorphic property, so you can check whether test cases are valid. In closing, where to go from there? So property-based testing and metamorphic testing, they don't need to know the expected input to know if the output is correct. So could we run them in production? You could, if you did that, get a new interesting metric, which would be properties violated divided by properties evaluated, instead of the general metrics that you get, which are, am I using too much CPU, which is quite important, but we don't have any metric that tells you your system is sane, your system is acting completely insane right now, you have to do something. Also, the interesting bit here is that instead of running your test on random inputs, you run them on interesting inputs. And they are interesting by definition because those are the actual inputs sent by your customers. So you know you are going to encounter that in real life because you have encountered them. So this is an idea I've been meaning to play with for ages. Haven't found the time yet. I've got kids, so not that many hours in the day. But I'm really looking forward to somebody else doing it and crediting me for the work. So please, someone. Then the next couple of slides are, in case you want to read these slides offline, it's me citing my sources. So these are good talks and papers for property-based testing. Great talks and papers about metamorphic testing and metamorphic relationships. You can find the slides are already available there. You can follow me on Twitter. You can get in touch with Besido if you want to work in Paris. And yeah, I always put that one, as this has been done using remark.js and Rob Norris' amazing TUT. If you do Scala presentation, do yourself a favor, use that. It makes your work so much easier. Do we have any questions? I hope we have some questions. We don't appear to have any question. So was that just really boring, or was that so clear that you guys got everything? It's absolutely crystal clear, and you're going to go back to your work after Scala Word and start doing property-based testing. Oh, that's a question. Amazing. Yes, thank you.
I have a question. So I've done a bit of property-based testing, but usually only like testing pure functions without side effects. But it sounds like you also apply them to real databases, maybe staging environments, or like apply them to systems that have side effects? How do you do this?
Right, okay, so I'm going to repeat the question so that the mic gets it and ends up on the video. So what I've shown of property-based testing, and what most people do with property-based testing, is testing pure functions. But I have hinted a few times that you could use property-based testing to test impure functions or stateful systems. And how does that work? Is that a fair representation of your question? Right, so I don't know about all the property-based testing frameworks in existence, but I do know about QuickCheck in Haskell and ScalaCheck in Scala. And both of them have an API called the Command API for ScalaCheck, and I forget how it's called for QuickCheck, probably the same thing, which allow you to simulate a stateful system. And so what you have is a generator of the initial state of a stateful system, and then you have a list of possible commands, that, hence the name of the framework, possible commands that you can apply on that system, and the properties that you should have after every single step in the system. And so what happens when you run that is you run your real system, your real stateful system, and your mock, really, of the stateful system in parallel. And as soon as something is validated, then you have a failing test case. And then you shrink that to the smallest possible test case that can fail the system, and then you get your answer. If you want to learn more about that, I think I linked that in the sources. John Hughes, yeah, testing the hard stuff and staying sane. I think this is where he introduces the concept. John Hughes is an amazing speaker. He's just lovely to listen to. So do yourself a favor and listen to that. He's going to answer your question way better than I could ever hope to do. And you're going to learn a lot more. Yes?
Have you used some good experience with mutation testing in combination with property-based testing?
Right, the question is, have I used mutation testing in combination with property-based testing? I have not. I have not used mutation testing much. I do want to, because it's very exciting, it's very interesting, and now we have a very good implementation in Scala. I think it's called Striker, which allows.
I've only experienced in Java.
But Striker is also Java, I think. And the concept of mutation testing is, well, you take your test, you make sure they pass, and then you subtly mutate your core source code, run the test on it again, and make sure that at least one test failed because you have, say, flipped a comparison operator, or where you had a plus, you've put a minus. And then that should break the system. And if it doesn't, then your test suite is not good. And so this is extremely interesting, I think, if you're in an industry where the cost of a bug is massive, but it's very expensive to set up mutation testing, because I mean, you've all used SBT. If you have to mutate your system 100 or 1,000 times and then re-instantiate SBT to run the whole thing, that's going to take some resources. It's getting better. I mean, we have bloops to help with this kind of thing, but still, it's quite expensive. So no, I haven't done it. If you know of anybody that has, please tweet about it, and I would be delighted to read about it. Yes?
Not so much my question, but another example of something that is quite useful to do that kind of exercise. If you have, say, like database evolution scripts,
Right.
kind of like apply the changes, then roll it back, and then know that ultimately if you apply it again, then at the end you still kind of have a consistent. You tested your rollback scripts, and you tested actually that applying will give you consistent on the change.
Right. So another example of, I'm trying to think of which category of property that would be, and right now I'm a bit fried, so I can't come up with it, but somebody will say. When you have database migration scripts, and well, one interesting test is to run all the database migration scripts, then roll them back and make sure you're still in the same state. Is that what you mentioned? Right, so that's probably in the list of categories of properties I gave you before. Right now, I can't think of which one, but I'll certainly think about it. And I think that's it. Thank you very much.